Hi, my name is Danishur Hemans. Today I will presenting my MSc dissertation project, that is AI and network traffic performance prediction using first packet regulations on the UNSW NB15 dataset. UNSW NB15 dataset means University of New South Wales Network Based 2015. This work was supervised by Fudge Sabri. Now I'm going to move to the table of content. I will walk you through the presentation in a clear order. We will start with the background and problem, then move on the aim, objective and research question. After that, I will cover the methodology, system design and result. And finally, conclusions and future work. Background and problem statements. So question is that why is the problem important? In modern network, especially in local area networks, predicting traffic accurately is a critical for efficient resource allocations and also maintaining quality of services. The issue is that most traditional methods are reactive. They only analyze traffic after the flow has completed. That's too late for real-time decision making. So in this project, I introduce a proactive approach where we make predictions using only the first packet of a network flow. The three key metrics I focus are total packet counts, total bytes, and flow durations. Here is a simple local area network setup. Now, research aim and objective. This research aims to develop and evaluate regression-based machine learning and deep learning model for predicting continuous per flow network traffic performance metrics using first packet data. To achieve this, the five objectives were critical review, key network performance metrics, and flow-based analysis. This means I look at a key performance indicators like packet count, total bytes, and flow durations to understand what actually matter for network performance. And second, compare classical machine learning and deep learning methods for first packet predictions. I compared both simple models and more advanced ones to see which approach worked best for this type of prediction problems. Prepare the UNSW NB15 dataset with first packet feature engineering while pretending data leakage. This is very important. I make sure the model only use information available at the first packet, so it doesn't accidentally cheat by using future data. And then the fourth one is implement and compare linear regressions, XGBoost, MLP, and residual models. I implement linear regressions, gradient boost, multi-layer perceptions, and residual network covering both traditionals and deep learning approach. Is evaluate model performance using mean absolute error, R-squareds, and symmetric mean absolute percentage error, and recommend the best model for local area networks. To guide the work, I define five research questions, mainly focus on which network performance metrics are more suitable for per flow analysis and how can they be reliably measured? Basically, which network measurements are most usable for predicting flow behavior? Then we have which machine learning and deep learning algorithm perform best for the first packet predictions. So I could identify which algorithm give the highest accuracy and reliability. The third one is what pre-processing and future engineering techniques best support first packet regressions. Which regression model achieve the highest accuracy for first packet counts, bytes, and durations? How can the best model improve capacity planning and quality of services in local area networks? This connects the research to real world use like better bandwidth allocation and reducing congestions. So overall, the goal is not just accuracy but practical impact in local area network. Literature review showed that the traditional statistical methods have significant limitation in modern local area network. The majority of UNSW and B15 studies focus only on classifications and intrusion detections. Very few addresses regressions and almost none use first packet predictions. The table show how my work filled this first packet regression gap. I follow the cross-industry standard process for data mining methodology because of its structured and iterative approach, which is ideal for data-driven regression projects in networking. All six phases were followed consistently. Here is the cross-industry standard process data mining models. I follow six phases. It provides a structured step-by-step approach for solving data science problem like business understandings, then data preparations, and then applying modeling and evaluation metrics, and then the deployment. Architecture design. The complete first packet regression pipeline is shown here. A strict first packet constraints was enforced to ensure zero data leakage. Three continuous targets are predicted from features available only at the initial packets. Let me show the better pictures of this. This diagram shows the full pipeline. key point here is a first packet constraint, meaning the model only use features available at the moment the first packet arrive. To this ensure there is no data leakage and make the system realistic for real-time use. The next step is data preparations and first package feature selection. I told that I use the UNSW and B15 dataset filtered down to about 93,000 normal flow. The target was total packets, total bytes, and flow durations. And I select 16 feature packets that are available as soon as first packet arrive. These include protocol information, port number, packet size features, TCP window size, time to leave values, and timing related features. I also created additional engineering features from port to improve predictions like well-known are HTT, HTTPS, FTP, and SSH, and time to leave operating system flags like Linux, Windows, and Cisco. Then pre-processing steps includes label encoding. This converts categorical value like protocol and or services into numbers so machine model can process them. Then we have log transformations. This reduce extreme sequence in data because network traffic has many small flows, a very few large ones. Then we have a scalings. This standardize the values so all features are on the same scales, which help model, especially neural networks, learns better. I split the data into training, validations, and test sets to ensure fair evaluation and avoid overfittings. All of this was done carefully to avoid data leakage. Now I'm going to move model implemented. So five regression model were implemented and trained on identical data. First of all, we have naive main. This is simple. This predict the same average value for all flows. It's a simple baseline to compare against. Then we have linear regressions. This is a basic model that assume a linear relationship between input and output. Then we have a gradient boost. This is a powerful tree-based model that builds multiple decision trees and combine them for a very high accuracy. Then we have a MLP. This is a standard neural network that learns complex pattern using layers, multiple layers. Then we have residual networks. This is a deeper neural networks that use skip connection to improve learning and stability. Now I'm going to move some development explanation. Now I will demonstrate the actual working projects I developed and trained the entire projects in Jupyter Notebook on Kaggle. Here is the library imports, then global setting for the graphs, and then data loads. Here is a pre-split data loads, and then split against over here. And then we can see the number of 93,000 data and 45 columns, and we can see different features that I explained already in the slides. Here is the target variables, total packets, total bytes, and flow durations, missing values checks, and in duplicate row checks, everything okay. So here is the exploratory data analysis, total packet distributions. We see here the right sequence we can see here because of medians are 18 and mean is 860. So we need to be apply log transformations to make the data like sequence. Here I applied a log transformation. We can see the sequence was R7.4. Now it's become sequence 0.29. So it's mean the data is now a sequence. Then protocol distribution check. 72% TCP protocol are used, and then UDP is as 23.7% used, and REP protocols are 4.1. Rest of the things are less than 0.5. So mostly protocols using 72%, that is TCP. And then I check some comparison like mean packets and total bytes. We can see when the total bytes it's increased, the packet of size also increased. And then pairwise correlations. Here is target verifications like if the packet size increase, bytes increase, but packets it's not directly depends on durations. We can see it's low, and bytes is also strongly not depends on durations. So we need to be check that the duration is most difficult to be predict because it depends on user behaviors. Here is a long transformations applied on total packets, total bytes, and flow durations. We can see there after the applying of log transformations, duration is still near to the zero. It's mean it's a very difficult to predict. And then packet feature selections. Have I talked about first packet feature sections already in these slides like destination ports, protocol, state, services, source to leave, destination to leaves, and destination window size. These all are already I explained in my slides. Pre-processing and feature engineering. So have explained like all the categorical data convert into integer, so machine can easily understands. Then we have operating system flags like Linux, Windows, and Cisco, and then any replace infinite value into a column medians, and then I split a data into three, like trend 70%, then validations are 15%, and test are 50% to ensure data is correct, validate, and no data leakage over there. So here you can see a graph to split the data like train 70%, validation is 15%, and then test is a 15% data. Here is evaluation matrix. I apply different evaluation matrix like mean absolute errors, R squares, and mean absolute percentage error as well. So here's the different models. I have already explained in this slide. I'm just going to go through knife based lines. Here's the result of knife based lines for the total packets, so for the total bytes and flow durations. Then the next model is a linear regressions. Is the result of linear regressions model. Then I train a XGBoost. Here's the result of XGBoost models, and then we have is for the packets, and the result for the bytes, total bytes, we can see 0.9988 is a good, and then we have only 0.1% error is for the durations, 18% error. Here I train multi-layer perception models. We can see the result of multi-layer perception here when I train residual neural networks, and the got result from this model over here is errors, mean absolute errors, and the R squares. And result summary, if I'm talk about the total result, we can see here. Then we can say the evaluation visualizations about the metrics. First of all, we have R squared comparison bar chart. Over here we see the gradient boost perform very well, all about the total packets, total bytes, and as well flow durations. Residual networks and multi-layer perception perform very well for the total packets and total bytes, but not good for the flow durations. Then we have symmetric mean absolute percentage error. So we can see the total packets boost applying very good, and then we have total bytes green boost applying very good, like only have a few percentage error. But during the flow durations, green boost have 18.9% error, but it's better from the rest of the difference models. So it means it's good for the others. If I talk about the model recommendations, so we can see the XGBoost performs best for total packet, total bytes, and flow duration as well. So we can see the total package XGBoost has R square 0.9984. It's mean it's very close to 1. Then we have about error is only 0.3%. It's less than all other models. So then we have total bytes. We can see 0.9989 R squares, and the error is only 0.1%. Then we have our flow durations. R squares are 0.9364, is very near to the 1 value, and then errors about 18.9%. It's less than all other models. So it's mean the model recommendation is XGBoost is performed best comparison with the others. Returning to the result slides, the model performance comparison table show that XGBoost achieved the highest predictive accuracy across all three targets. It delivered excellent R squares values and very low error rates on the held out test data. These results confirm the effectiveness of the first packet regression approach. Now I'm going to move discussion and key insight. The analysis show that gradient boost achieve the best balance of accuracy, speed, and interpretability. First packet regression enabled truly proactive network management in local area networks. The log transformation successfully addressed the sphere sequence in the flow data. Features important analysis provide valuable insight for network engineering. And overall, the results support the practical deployment for improved quality of services in local area network. If I am talk about conclusions and future works, in conclusions, the research aim and all five objectives were successfully achieved. XGBoost is recommended as the most suitable model for these applications. The study provides the first comparison for first package regression pipeline on the UNSW and B15 datasets. This work contribute a practical solution for proactive traffic management in local area networks. So if I'm talk about the future, in future work, this could be extended to a real-time deployments and adaptive model that learns continuously from live network traffic. Thank you very much for watching That's it for my sides. Bye now.